Okay, welcome everybody to this second iteration of SPCL Bcast. We are really honored that Amir Gholami and Zhewei Yao are going to talk about AdaHessian today. And without further ado, I'll give to Nikolai to introduce our two speakers today.
Okay, thank you, Torsten. And again, thank you everyone for coming. So Amir is a senior research fellow at the Berkeley International Computer Science Institute and Berkeley AI Research. He received UT Austin's Best Doctoral Dissertation Award, is a Meloche Medal finalist, and has received numerous Best Paper Awards. He was also part of the NVIDIA team that helped make half-precision training possible. He is also joined by Zhewei, who is a PhD student at Berkeley AI Research, working with Michael Mahoney and Kurt Koitzer. He received his bachelor's in mathematics from Xi'an Honor College at Shanghai Jiao Tong University. And now I'll let Amir and Zhewei tell us all about second-order methods and AdaHessian.
Okay.
Yeah.
Thanks so much, Torsten and Nikolai, for the nice introduction and for the invitation and giving us the opportunity, as well as everyone who's joining. Please feel free to ask questions in the middle of the talk. So today we'll be describing the work that we've recently done on second-order optimizers called AdaHessian. It's an adaptive second-order method for machine learning optimization. And this is a joint work with several of our colleagues, including Sheng Shen, who's a first-year PhD student, Mustafa, who's a research scientist in Lawrence Berkeley National Lab, my postdoc supervisor, Kurt Koitzer, and Michael Mahoney. So let's get started. So what's the 1-minute executive summary of our work? We're proposing a new optimizer that uses second-order information. And in particular, we are able to get very good accuracy on several modern neural networks. So we're not testing simple, shallow networks. We're actually testing kind of state-of-the-art models for each of the different learning tasks, and we're getting significantly better results than other adaptive optimizers. In computer vision, we're able to get more than 5% better accuracy compared to Adam on ImageNet, and we are on par with SGD. And I should say that this is actually one of the first optimizers that's achieving the same performance as SGD on computer vision tasks, and significantly better than Adam. On NLP, actually, we get significantly better than SGD and up to 1.8 better perplexity than the best optimizer called Adam W. And we even tested this on recommendation systems where we get 0.032% better accuracy than AdaGrad. This number is a little bit smaller compared to the other ones, but for recommendation systems, this is the order of accuracy improvements. And what's the basically ideas? So there's two ideas. There is a low-cost Hessian approximation using Hessian diagonals, which is actually applicable to a wide range of neural networks, and you don't need a very complex machinery to code this up. The other one is a novel temporal and spatial smoothing scheme to reduce Hessian noise across iterations. So this is very similar to what we're doing with momentum for SGD. So when we're applying momentum, we're basically computing a momentum for the gradient. This is an equivalent version of it, a somewhat equivalent version of it for computing the momentum of the Hessian. So why is this really important? So taking a step back, we all know about the cost of hyperparameter tuning. There has been several different methods that have, claimed to be hyperparameter free. But the reality is this is one of the problems with neural network training, that there's so many different hyperparameters, and some of them are beyond what we usually talk about, which is learning rate or momentum. Even the seed that people use to train is a hyperparameter. So for example, Zhewei knows about this story. One of the papers that had very good results, we knew the authors and we were trying to reproduce their results and we couldn't. And when we went to them, because they were our friends, we said, these are the runs that we're making and we're not getting anything close to what you have. And then he said, you have to tune even the random seed. And that's a big problem in neural network training. And the problems are not just that, we want to train ImageNet in a few seconds. The problems are the new neural network models, like, these BERT models, they take weeks to train. So even for big companies with a lot of resources, it's not really possible to tune all of these hyperparameters and the random seed. But to make the thing worse, even the choice of the optimizer has become another hyperparameter. So if you actually look at different learning tasks, such as computer vision, NLP, and recommendation systems, you see that for image classification, SGD performs a lot better than other methods. If you apply Adam or Adam W, the performance is significantly worse. And so maybe you find a paper that shows that Adam can work as the same as SGD for a shallow neural network, but once you test modern neural networks, you see that there is a very, very wide performance gap, as we will show. For NLP, on the other hand, the performance gap is even larger between SGD and Adam. So if you apply SGD, you get significantly worse results compared to Adam. And the difference could be up to 50 points, as we're going to show. And for recommendation system, the performance of AdaGrad is typically better. So even the choice of the optimizer that you have, along with the learning rate schedule, the learning rate, the random seed, all of these have become a hyperparameter, and that's not really good. So let's get started and see how AdaHessian is an initial attempt, or is a preliminary attempt to addressing this problem. So let's define some notation. We're going to denote the loss with E. The model parameters are denoted with W. We're considering a supervised learning task where we have n samples, xi, for which we know the label. And we're trying to minimize the average cost or the empirical loss on n examples. How do we do the training? Well, we have a loss landscape. We have some loss function that we're trying to minimize. We start with some random initialization of our weights, W0. We compute the gradient of the loss with respect to the parameters, and we go in the negative direction of the gradient. So I take a batch of examples B, compute the gradient, go with the step size lambda, and go in the negative direction of the gradient. And then you repeat this process. Now, there is a fundamental problem here in that this lambda should not be the same for all the layers. So let's consider a very simple, hypothetically, overly simplified case where we are only considering y equal x squared as our loss landscape. So let's consider you have your ResNet. Let's consider that the ResNet has 20 layers. So this is the input, this is the output. Let's hypothetically assume that every one of these layers had only one parameter instead of many thousand. And the loss landscape corresponding to that one parameter was a parabola. So let's say the first layer would look like y equal 0.1x squared. So if I keep everything else constant and only perturb the first layer, I'm going to see this parabola. For the middle of the network, maybe I see y equal 4x squared, and at the end I see y equal x squared. The problem of using the same lambda for all of these layers is that the curvature differences require different step sizes. So why is that? For example, consider if all of them are at the same point of -4. So if I'm at -4 for this curve, 0.1x squared is really flat, and I have to take a large step size to get to the optimum point, which is 0. And the gradient is smaller. But if I'm at the point -4 here, the gradient is significantly larger. So if I use the same step size multiplied by that gradient, I'm going to overshoot the point 0. So if I'm using the same step size, irrespective of the loss landscape, I'm going to have a suboptimal descent algorithm. Now, there is a solution to this, which is second-order methods. They have been invented many, many years ago. They're widely used in scientific computing applications. And the idea is very simple. We can precondition the gradient to avoid this ill conditioning of the different directions. So the update formula looks the same as first-order methods, except that you apply a preconditioning matrix. So let's denote the update formula to be the new W in t+1 iteration is going to be the old W minus a step size times the direction. So for first-order methods, this direction is going to be the gradient, and this eta, depending on whether you're doing SGD or Adam, could be just a simple scalar or a scalar divided by a first-order correction. Now, for second-order methods, instead of just using G, you precondition G by multiplying it to H inverse. And that enables you to correct for these curvature differences up to a second-order derivative. So how does this work? For example, for this curve, if you look at the Hessian, going back to our simple 1D example, 0.1x squared has a second derivative of 0.2. So if I apply H inverse for that, it's going to be 1 over 0.2 times the gradient. So I'm going to basically have a step size that's 5 times the gradient. So if I go back to the example of -4, if I'm here, even though the gradient is small, H inverse is going to magnify that by a factor of 5 so that I can take a larger step size. On the other hand, if you have a sharp loss landscape, like 4x squared, the second derivative is going to be equal to 8. So take the second derivative of this, it's 8 everywhere. And if I compute a gradient, it's going to correct the gradient step size inversely. So it's going to reduce it by a factor of 8 so that I wouldn't overshoot this point 0. And in fact, for a parabola, the second order methods converge in just one iteration. Now, another very simplistic example, you can consider this in 2 dimensions, where your loss landscape is a ellipsoid, x squared plus 10y squared. So now you're basically, your loss landscape is changing more rapidly along the y-axis. So that's basically, this has a condition number of 10. So that it's not like a simple, a circle. So here, if you're applying second order methods, this is still a parabola, it will converge in one iteration. So let's have this starting point. If you apply H inverse times G, this is what you see. It converges in one iteration. But if you're applying gradient descent, well, you take a step along the gradient direction, then you take another step, etc. And it takes many iterations to converge. And if you actually use gradient with momentum and you tune the hyperparameters, it actually won't converge in the same number of iterations. So what does second order methods or full Newton method does? Full Newton method performs rotation and scaling of the gradient vector. So if you're at this starting point, this orange is the direction of the gradient. When you apply H inverse, what is happening is that it's rotating the vector. So it's rotating it to basically point it across the local optimum using the second order approximation of the loss landscape. And it's also scaling the step size to correct for this ill conditioning of the problem. So that's what full second order methods do. Now, okay, so in one dimension, everything is simple, but how do we deal with the Hessian in the higher dimensions? Well, if you have higher dimensions, the gradient is going to be a vector of size number of parameters. So, for example, for resonant 50, we have 24 million parameters, and the gradient is essentially a vector of size number of parameters, which is 25 or 24 million for resonant 50. Second order derivative is the rate of change of the first derivative across all of these directions. So it's going to be a matrix. So the first row of the Hessian is going to be the rate of change of the first derivative along the first direction. The second entry is the rate of change of the gradient along the second direction, and so forth. So this becomes a matrix of size number of parameters times number of parameters. And this is definitely prohibitive to form. For resonant 50, this is going to be order billion parameters, and definitely very difficult, if not impossible, to compute its inverse. So we have to find approximate ways to apply H inverse, and that's not very hard because there's a lot of work on randomized linear algebra. But for 1 second, let's consider that we put this problem aside. If you had Hessian, what can we do? Well, if you have the Hessian along with the gradient, you can kind of open up the black box of the neural network in terms of the loss landscape at least. So what can we do? For example, consider a simple neural network where you have an input X, you have an output Y, you have n layers. And this could be a bird model, it could be a CV model. And every one of these layers has, for example, different multi-head attention or different convolution. What we can do, if we had access to this Hessian and gradient, what we can do is essentially probe the loss landscape of each of these parameters individually. So for example, if you consider this case, what we're plotting is the loss landscape when we're keeping the parameters of this convolution layer constant. We vary the parameters of this convolution, and we keep every other parameter constant. So basically, we're just perturbing the parameters of this particular convolution along 2 different directions. So along the first eigenvector of the Hessian, which is along the epsilon 1 direction, and along the second eigenvector of the Hessian, which is epsilon 2 direction. So everything else in the model is constant. And then by perturbing the parameters along those 2 directions, we can get the loss landscape. So you see the loss landscape, for example, for this convolution channel is particularly very sharp. And the last one, if you repeat the same thing for the last one, you see that it's really flat. And this can give us a lot of really good information. For example, you can use this for quantization. You can use this for reduced precision training. You can use this for pruning. You can use this for correcting the step size. And that's what AdaHessian does. But as we said before, this Hessian is a formidable matrix. So we have to find approximate ways of applying the Hessian. Well, the most simple thing we can do is to use the Hessian diagonal. So let's ignore all of the off-diagonal structure for a moment. What we can do is, instead of looking at the full Hessian, let's just approximate the diagonal of the Hessian and see if we can do a better optimization algorithm with just this much more information. So we have gradient for first order methods. Let's see if I give you a little bit more information about the diagonal of the Hessian. Can you do better? Well, this is a lot of advantages because actually when we have the Hessian diagonal, it's like a vector. So we can apply the momentum very simply without having to store an n squared Hessian matrix, which we're going to see it's going to be very, very useful. So with this, what can we do? Well, let's look at the Adam formula. In the Adam formula, when you have the new parameters, it calls it to the old parameters, minus a gradient momentum divided by a correction term that basically is trying to adaptively change the gradient. So the gradient momentum term is the same as Adam. So basically, you're computing an exponential moving average of gradients over iterations. But for the second, so-called second moment, Vt, Adam uses gradient, so gradient dot gradient to scale the learning rate. Instead of using the gradient, we can use the second derivative to basically scale the momentum. And if you think about this formula, it kind of looks like the diagonal of H inverse times the gradient. So essentially, think of H as a diagonal matrix. H inverse is going to be 1 over diagonal. You're using that to scale the gradient. So you're basically adaptively correcting the step size. So the formula is exactly the same as Adam, except that for the second moment, we are replacing the first order correction with a second order correction. And for that, we're using the Hessian diagonal. So this basically compares what's the difference between different optimizers. For SGD, there's no second derivative, there's no second moment, so no correction for the learning rate. You're marching along the momentum. For AdaGrad, you're not using momentum for the gradient, so you're always using gradient at every step. And then you're correcting the second derivative, you're correcting the second moment with GG. G basically the dot product of G, the element-wise product of the G's. And this is a problem, well-known problem of vanishing step size because you keep accumulating something in the denominator. So this is basically your output formula, eta times mt divided by v. And this v keeps growing and growing and growing. And as a result, you have a vanishing step size. So you get stuck. You lose momentum at some point. Adam and RMSProp tried to address that by introducing momentum for the gradient and momentum for the second moment. Basically, they're computing an exponential moving average so that this v doesn't just grow, grow monotonically. And AdaHessian uses the exact same formula, except two things, except using the Hessian diagonal to for the second moment, and also a parameter k here, which is essentially the power of preconditioning, which usually this k is equal to -1 for full Newton method, and it can be less than -1 as well. So going back to the elephant in the room, how can we actually approximate this Hessian diagonal without forming it? Well, we can use the Hutchinson's method, and there is a very good paper by Yusuf Saad's group where they explain how you can approximate the diagonal of a matrix without forming it. And the idea is very simple in Hutchinson's method. So consider any matrix. It doesn't have to be the Hessian. We can approximate the diagonal of this matrix by computing an expectation of z, Hadamard product with h times z. So z is a random vector. It can be a Rademacher random vector or a Gaussian. Rademacher has better variance in the error. So Rademacher is essentially -1 and 1. You draw a random vector z. You multiply the Hessian with that random vector z, hz. That gives you a vector. You compute the dot product between the pointwise product between the random vector, the original random vector, and the application of h times z, and an expectation that converges to the Hessian diagonal. And this holds for any matrix, and you can try this for yourself in a few lines of Python. So for computing this diagonal, in particular, we don't have to have h to multiply h with z, right? We don't have to have h formed explicitly and then multiply it with z. We can actually do it in matrix free. So how does that work? Well, that works very simply. That works with a single additional backprop in the network. So the way that works is that when we draw that random vector z, we can compute the dot product between the gradient that we have and that z. So that's going to give us a scalar. And then if we backpropagate that scalar, which is similar to the loss, for example, which is a scalar, if you backpropagate that throughout the network, that's going to be equivalent to multiplying the Hessian with this random vector z. So why is that? We can expand this formula here. So dg transpose z d theta is going to be equal to dg d theta times z plus g times dz d theta. Well, z is a random vector, so this term is 0. And dg d theta is equal to the Hessian. So this essentially gives us Hessian times z, and Hessian is symmetric. And so Perelmutter has a very interesting and very, I highly recommend this paper, very interesting way of explaining this in his paper in 1994. So this is not new. And once we have this h times z, we can plug it in here and compute essentially an approximation to the Hessian diagonal. And so we have a library called PyHessian that explains how you can do this very efficiently. And you can even do this on your laptop for ResNet 50. So it doesn't require a supercomputer to compute this. And once we have that, we can essentially plug it into the Hutchinson method, get the diagonal of the Hessian, and plug it into the AdaHessian formula. So now let me hand it over to Zhewei, who's going to explain the second part of the novelty, which is the momentum. Zhewei?
Yeah, so thanks for Amir's introduction part. So first I will say, like Amir mentioned a couple of times, that we use like the same formula as ADAM, and we know the most important thing for ADAM is like the adaptive like learning rate part, and also the moving average. So the first question is that, like, why do we need like the momentum for like the second order information? Since if you know like Newton method, typically Newton method always do like the H inverse G for the local step. So this will cause some problem for neural network training or for typical non-convex problem training. So here we show a very, very simple 1D example. So fx equals x squared plus 0.1 x sine x. So you can see overall it's still like a quadratic function. However, you have a lot of like local noise, like this 0.1 x times sine x will give you a lot of like local noise. So you can think this local noise is come from like the non-convexity of your problem, or like, for example, the mini batch noise, since you know like for mini batch you will get some like noise. So here we see like if you don't do second order momentum, so the orange curve, so you from like the start point, roughly I think x equals 3, and then you will start at some like local minimum about like x equals 1 point something. So if you use like the second order momentum, so basically what we do for AdaHessian, so the blue curve. So as you can see, even you have like tons of like local noise, your loss landscape is very sketchy. You can still converge in roughly like 7 iterations if I don't count it wrong. So that's basically like the core, one of the core idea of like our AdaHessian paper. So instead of using the traditional like always like the local Hessian information, try to capture the global Hessian information. And later we will also discuss this when we help you to reduce your computational costs. And the second part of the AdaHessians, like the novelty of AdaHessian is the spatial averaging. So what is spatial averaging? So one thing we haven't mentioned is that like we do the Hutchinson method 1 iteration per update. So basically, instead of compute like the diagonal of your Hessian to be a very precise, like accurate, we only do it like very like coarsely for one iteration per update. So as you can see that it will introduce some like noise. So how can we reduce noise? Of course, the moving average can help you to reduce noise. Another thing we can do is do the spatial averaging. So basically, instead of look at like every single dimension, you group some dimensions together and look them in like, and look them at entire parts. So here, like for a very simple example for like a convolutional kernel. So typically a convolutional kernel is 3 by 3 times like n. So n is kind of like your channel size. So if you think like the 3 by 3 is your kernel size, so instead of like look at like this 9 dimensions like independently, you can look at this like 9 dimension as like as a whole. So what does that mean? So instead of like, what does that mean? It basically means like when you compute the Hessian diagonal of these 9 elements, instead of directly apply them, you compute the average of them first, then apply this average to all of them. So how can this one help in your training? So here we show like one example on the machine translation task. So one is like the use block size one. Basically, you treat each dimension independently. So as you can see, the Hessian information has some noise like over your whole training from iteration 0 to iteration like 16K. However, if you use like block size 32, the orange curve, so as you can see, the noise reduced a lot. So this one can further help you to like kind of like smooth your like Hessian information or the curvature. You may think, yeah, you add a lot of tricks to your like this is kind of a trick. However, in later we will show that like this like hyperparameter is not such sensitive. Also, if you want to get the best result, you need to tune it. But if you just want to get the state of the art result, so state of the art here means like the best result the previous optimizer gets, you don't need to tune it at all. So has this like two tools in our background. So we will show the result of AdaHessian on different tasks. So the first thing we show here is the most tested task, the image classification, and we use the ResNet, one of the most famous network on CV, on CFART and ImageNet. So first we can see here like the original the default optimizer for this task is SGD. So as you can see, it achieves better results than ADAM or ADAMW, which typically for now is the default optimizer for NLP. So the gap is roughly varies from like 1% to roughly like 0.5%. However, the gap becomes larger on ImageNet. So SGD is roughly 6 or 5% better than ADAM and roughly 2.5% better than ADAMW. So as Amir showed, or as I showed like before, like AdaHessian uses almost exact formula as ADAM. However, just replace the second momentum from gradient to Hessian. You can see the result of AdaHessian is comparable, even better than SGD on CFAR10 ResNet 20 and ResNet 18 on ImageNet, and slightly worse than SGD on ResNet 32. So briefly, it's like AdaHessian's performance is the same as SGD. So one thing we want to mention here is that we know like SGD is like heavily tuned, and we don't have the resources to AdaHessian for those like typical tasks. So for the second thing we want to show is for like the NLP task, which is like after BERT or after transformer is one of the hot topic. So here, like ADAMW is the default optimizer, and as you can see here, like SGD performs much worse than ADAMW. So on IWSLT is roughly like 7 points worse than ADAMW, and on WMT it's roughly like 2 points worse. So however, if you like change like the optimizer to AdaHessian, you can still get like performance gain. So it's roughly gain like 0.13 on IWSLT and roughly 0.33 on WMT14. So here we still want to mention that like except the learning rate, as you know, like for different optimizer you need to tune the learning rates and the block size. So basically the spatial averaging block size is tuned for AdaHessian. All the hyperparameters are like fixed. So basically AdaHessian uses the same hyperparameter as ADAMW. For example, the dropout rates, the warm-up iterations, and all of those things. And then you may wonder like if we cherry pick like this task for AdaHessian to beat SGD and ADAMW. So we also show examples on language model. So another task on NLP, but roughly I think the same model, the transformer model. So as you can see here, the same thing happens for SGD. So it performs much worse than ADAMW. So typically for Wikitext 103, the performance drop is more than 50% or 50 points worse. So replacing AdaMW with AdaHessian, you can gain like 2.7 points on PTB and 1 point on Wikitest 103. And the same thing as previous slides. So we don't do anything except the learning rate and the spatial averaging block size. So typically when you're talking about like NLP, people will ask you, so do you have test algorithm on BERT model? So the answer is yes. So here we try our algorithm on the squeeze BERT fine-tuning on GRU task. So GRU task roughly has like 8 or 9 tasks, and except one or none of them, we test all of them. So one thing we have to admit is that AdaHessian is not the global optimizer or the universal optimizer. So as you can see here, for some of the tasks, AdaMW works better. So for example, SST2, QNLI, QQP. So one thing I forgot to mention is that the first column, the ADAM, and with the plus sign or the dagger sign, is directly from the author's paper, and the AdaMW with a star sign means what we reproduce. So as we can see here, by although the 3 tasks AdaHessian works worse, but for the rest of them, AdaHessian works much better. So for example, for the RTE and the MPRC, AdaHessian has more than 1 point gain against AdaMW. And overall, the average performance of AdaHessian is roughly 0.4 better than AdaMW. So as you know, usually since except I will say the BERT model, the performance gain for different models are roughly 0.3 or 0.4. So instead of changing your model, it's just changing your optimizer can also give you the same gain. So the final task we have tested with AdaHessian is the recommendation model. So we tested on the with the DLI model on the critical Kaggle datasets. And here the default optimizer changes. Instead of use SGD or ADAM, for now people use AdaGrad. And AdaGrad typically gives you the best result. So however, using AdaHessian can even improve the results against AdaGrad on this task. So on the left-hand side, we plot the training and the testing curve. Although the training curve they are almost identical, the testing curve you can see the difference. So after roughly 200K iterations, you can clearly see the performance of AdaHessian is above AdaGrad. So that means maybe AdaHessian can avoid overfitting since the training curves are almost identical. So at the end, the performance gain of AdaHessian is roughly 0.032. As Amir mentioned, although this gain seems very small, but this typically is the gain for the gain level for recommendation system. So next I will discuss 2 important things. So one is the computational cost, another is the robustness of your optimizer. So first look at the computational cost. So people usually think second order method will be extremely expensive as compared to first order method, since for example, when you need to compute H inverse G. So this requires a cube computational cost and a quadratic memory saving. However, since we are using the diagonal of the Hessian, so the quadratic memory is reduced to linear. The second part is how do you the second question is the computational cost. So here we show example on ResNet of ResNet 20 on CFAR10. So first thing we want to say is theoretically the computational cost of AdaHessian is roughly 2x as SGD. So the 2x comes from the additional backpropagation to compute the diagonal of the Hessian. And as we mentioned, like we only do the Hutchinson one step per iteration. So it's like the 2x as SGD. However, as you know, like the current framework is optimized for first order method, like for example, PyTorch, TensorFlow. So if you measure it like in the real world, you will see like the computational cost is higher. So for example, here like we measured like against SGD is like roughly 2.4x more expensive. And if you compare with ADAM, it's roughly 2.3 more expensive. So this like 0.4, 0.3 comes from like the framework. It's not optimized like for second order method. So here we also show like how can you reduce your computational costs. So a very simple idea is that like instead of compute Hutchinson or the diagonal, every step you can compute maybe like every 2 steps or every 3 steps. So every 2 steps basically means for like 2 consecutive like iterations, you only compute the diagonal for one of them. And for 3 steps is like the same thing. And until like for 5 steps. So as you can see, like we can reduce the computational cost, like theoretically to like 1.2x as SGD and achieve the same performance as SGD, or you can, or like in the measured cost, you can reduce to like roughly 1.25. So the keyword here is basically like the computation cost of AdaHessian is roughly the same as first order method. So second thing we want to discuss is basically the robustness. So typically people are struggling to like tune the learning rate. So here we show like one example on IWSLT comparing with AdaHessian and AdaMW. So we vary the learning rate scaling from 0.5 to 10. And 1 basically means you use optimal learning rates, like tuned like for AdaMW and AdaHessian. And 0.5 basically means you scale the best learning rate by 0.5. So as you can see, one learning rate is quite small, like range from 0.5 to 4. Both AdaMW and AdaHessian works pretty good. And to be honest, AdaHessian seems like more robust around this like small range. However, when you go beyond like 5x large learning rates, the performance of AdaMW is almost like it's only better than like random guess. It's only like 10 points. And if you go to 6, AdaMW already kind of diverge. And if you go to 10, it's like indeed diverge. However, like as you can see for AdaHessian, the best performance and the worst performance, like the difference is like within 10%. And in the point value is like roughly 3 points. So this typically means like AdaHessian is like, if you want to try your model like in like in an initial stage, using AdaHessian can help you to tune your model, like the model architecture. And if you use AdaMW, you need to like carefully scale your learning rates. So the second thing for the robustness is like the block size. So we mentioned like the block size is very critical if you want to get the best result of AdaHessian. However, if you just want to beat AdaMW, you don't need to tune it at all. So here we vary the block size from 1 to 128. So as you can see, all of the results is above 75.6. And remind you that the AdaMW's result is 75.66. So there's a mistake. So basically all of the results of AdaHessian is better than AdaMW. And note that like we don't tune like the learning rate. So the learning rate of this like 1, 2, 4, 8, like all of those are the same. Also like the drop odds, all of those things. And we only vary like the block size. Yeah. So one thing we want to mention is that like there are a lot of works like to show like the first order method works very well. Like for example, like the paper from Michael Jordan said like the first order method can like escape the saddle points. And also like a lot of papers discussing like how like gradient descent can convert to like the minimizers and other things. However, some of the papers are also show like in practice, SGD is very brittle. Like for example, the paper from Penshi and like the Michael Mahoney. They mentioned that like in their like the practical in their like paper, they mentioned that SGD is very like sensitive to, for example, your like first of all, people knows like the learning rate, and also like for example the like initialization. So that's why like people want to consider second order method. So there are also a lot of work consider like using like second order method, like for example the paper from Yan LeCun, no more Peskin learning rates. And also the paper from Professor I forgot his first name, Professor Tong, like for example the batching LBFGS for like machine learning problems. However, the thing is that like the most of the current second order method, it cannot really train neural network. So it typically means like if you train on like ResNet or transformers, you will see some like performance like drop. And since there are tons of like second order method work, and if you want to look at them, we will suggest that you look at the last paper from North group, the optimization method for large scale machine learning. This is quite a good summary for most of the second order method. So in summary, so we like propose AdaHessian. So AdaHessian is like a new second order method typically for, I would say, for machine learning tasks. And we achieve state-of-the-art result on ImageNet and a new state-of-the-art result on NLP tasks as well as a recommendation system. And we propose two new techniques for second order method. One is using the momentum and another is using the spatial averaging method. So thank you for your attention. If you have any questions, you can ask them here, or you can ask them like through emails. And if you are interested in the like the Hessian stuff, so we have a tutorial online. It's called like the Hessian, and there's a tutorial. You can go with the tutorial to get familiar with the Hessian stuff. And we also have the tutorial for AdaHessian, and help you to like know more about AdaHessian and how to apply it for your own problems. Thank you for your attention.
Okay, thank you very much for the lovely talk, Amir and Zhewei. So we will take questions in just a moment. I do want to mention also that if you're interested in second order information and similar techniques, our next SPCL BCast talk on the 8th of October will be from Professor Ryo Yokota at Tokyo Tech, who will be discussing distributed deep learning with second order information.